In this video, we describe how to obtain the density of a gas from the ideal gas equation. Alright, so we have already introduced what the ideal gas equation is. It's just a relationship between four properties of gas, such as pressure, volume, number of moles, and temperature. Right, so the idea here is to try to calculate what the density of a gas then would be. When we think about density, okay, which I'm going to define using the Greek letter rho. Okay, so this letter is read as rho. Okay, that is equal to mass over volume. So the question is, how can we actually incorporate density into this expression? Well, the volume is already there, right? You have it right here. The question is, well, in what of these properties is mass involved? Obviously, you can think that the number of moles of a substance can be calculated simply by dividing the mass of the substance over the molar mass. Okay? So replacing this into the number of moles, we're going to be able to incorporate mass and then solve for the density. All right, so let's see how that works. So we have P, pressure times volume, is equal to the mass over the molar mass, RT. If now I consolidate terms right here by dividing both sides by the volume, okay, I get an expression which is like this, where this is going to be the density, obviously, and that is the molar mass, pressure, RT. Okay, so next step is the pressure is equal to the density, RT, over the molar mass. And finally, if we solve for the density, we find that the density of a gas is going to be equal to the pressure multiplied by the molar mass of the gas over R times T. Okay, so what we learn here is that the density of a gas does depend on the nature of the gas. It's going to matter if you actually have nitrogen or oxygen, because the molar masses are different, and that will affect the density as well. It will also depend on the pressure and temperature. Okay? All right, great. So let's actually run a couple of examples to see what type of densities you have in a gas. All right, so we can calculate what the density of N2 is at STP, right? So that is going to be a useful set of conditions of pressure and temperature. All right, the molar mass of N2, we go to the periodic table and find that the molar mass of N2 is equal to 28.01 grams per mole. Okay, so let's see how that works for the density calculation. After the pressure is going to be equal to 1 atm at STP, then the molar mass is equal to 28.01 grams per mole. And then we divide by R, 0.08206 atmosphere liter over mole Kelvin, and then multiply by the temperature, which for STP is equal to 0 Celsius, but we have to use it in Kelvin, which is 273.15. Okay, so let's see what the units of this result are going to be. Atmosphere cancels with atmosphere, mole cancels with mole, Kelvin cancels with Kelvin, and the only thing that is left over is grams over liters, so mass over volume. So that is correctly a density, right? So the density is going to be equal to 1.25 grams per liter. Okay. Now this is a really small density. Okay, if we were to do the calculation with water, okay, water gas, okay, the density that we actually have obtained for water gas under these conditions, and the density that you have if water was in the liquid phase, would be about 1,000 times different. Okay, so again, a general rule of thumb is to consider that gases at about 3 orders of magnitude, or 1,000 times less dense than a liquid is. Okay, so that is useful. Now we can compare this to a different gas. Okay, so we can repeat the calculation for instead of nitrogen, we can do it for a gas like helium, where the only thing that will be different is that the molar mass of helium is not 28.01. We go to the periodic table, and the molar mass of helium happens to be 4.002 grams per liter. Okay, so notice how the molar mass of nitrogen is about 7 times greater than the molar mass of helium. Okay, and that means that because the conditions are the same, we're going to still do the calculation at STP. The density of helium should be about 7 times smaller. Okay, so this is again to reinforce the notion that the density does depend on the nature of the gas. As a matter of fact, it depends linearly with the molar mass of the gas. This makes a big difference with the molar volume, which is, it does not have a dependence on the nature of the gas. Right, so I'm not going to set up the calculation. Simply the only thing you would do is just replace this by 4.002 grams per mole, and then the number that you get out of this should be 7 times smaller than the than the density of nitrogen, and this number happens to be 0.179 grams per liter. Okay, so to summarize, what we've done in this video is derive an expression for the density of a gas from the ideal gas equation, and we have calculated the density of the gas for a couple of examples.